My name is Hai Nguyen Nguyen. I'm from Imperial College London. I'm going to chair section 7. And the first presentation is motion planning, design optimization, fabrication of ferromagnetic swimmers, presented by Just Karen.
All right, good morning, everyone. My name is Jaskaran, and I will be presenting our work on motion planning, design optimization, and fabrication for ferromagnetic swimmers. So let's start with the motivation for this work. We are interested in making microrobots, which, due to their small size, provide non-invasive access to microscopic spaces. This means that they can be used in applications such as minimally invasive sensing and micromanipulation. On the flip side, however, their small size constrains us from having a lot of power and actuation on board, and also the control is non-intuitive. So keeping these ideas in mind, we present theoretical analysis and hardware experiments for an externally actuated microrobot that swims in a viscous regime to simulate how microrobots would move. We consider a simple two-link swimmer, each link of which is just a bar magnet that experiences a torque in an external magnetic field. And by orchestrating the components of the spatial time-varying magnetic field, we create undulations that ultimately result in swimming. So we derive a first-order model for the swimmer by incorporating hydrodynamic and magnetic effects, and then use this model to define motion primitives and define control inputs that result in motion along given directions. For this swimmer, the translational velocity depends on the angles of the links and the rates at which these angles change, which means that you can obtain the displacement by integrating this velocity. And it turns out that this displacement depends on the curl of this matrix J. We can visualize this curl in the form of a heat map over a two-dimensional θ1, θ2 space. And now let's say I want to synthesize a motion primitive that generates swimming along the x-axis of the world frame. All that I have to do is pick a loop, such as this blue loop in the figure, that covers non-zero area in the x component and zero area in the y component. It turns out that the magnetic field that results from using this blue loop has a constant component in the x direction and a sinusoidally oscillating component in the y direction of the world frame. And as this video shows, you indeed obtain translation along the x-axis of the world frame as we originally wanted. So now, using this control input, it turns out that the limit cycle that you get in the orientation angle space is locally asymptotically stable, which we prove using stroboscopic or a Poincare map. Which means that no matter what the initial orientation of the links of the swimmer is, once this control input is switched on, steady-state oscillation will always be obtained along the x-axis of the world frame. So we get this stability property for free and use this to prescribe behaviors such as tracking a rectangle as shown in this picture. All right, well, now that we know how to make the swimmer move along different directions in the world, we ask, how can we optimize the speed of translation? So for that, all that we do is pose a very basic optimization problem in which we query the magnetization ratio of the second link relative to the first link. And we find from our experiments, as well as from our simulations, that as this ratio of magnetization of the second link relative to the first link increases, the speed of translation increases. And that's simply because with greater magnetization, the link oscillates with a greater amplitude, displaces more fluid, and advances a greater distance forward. Now we use these design variables to fabricate an efficient and optimal swimmer. So what do? We take single links, which we custom make by mixing magnetic powder and elastomer. We magnetize a bunch of these links using a pair of neodymium magnets. And then to make sure that the ratio of magnetization is consistent with the one that we got from optimization, we do a timing test. And if it is consistent with the optimization, we patch these two links together. That gives the two-link swimmer. And then we conduct experiments with a Helmholtz coil setup, which generates magnetic fields. So this slide shows a sampling of some of the experiments that we did with the two-link swimmer. You get translation using different kinds of primitives, as well as turning in place type locomotion using different kinds of primitives. The video on the bottom right, however, as you can see, is a three-link swimmer. And the idea is just to show that a control framework for a two-link swimmer generalizes to a three-link system as well. We have more experimental results. And if you have any questions about this, please see me at the poster session and send me an email. Thank you.
The second presentation is collective formation and cooperative function of a magnetic microrobotic swarm, presented by Sao Quang Dong. Please.
Hello, everyone. I'm Xiao Guang. I'm going to introduce our recent work on a macro-scale robotic swarm. Researchers have long been working on large-scale robot collectives, which can be independent controlled for interesting cooperative functions and collective behaviors, such as parallel cargo delivery in warehouse by mobile robots, and the self-assembly into complex formations by the kilobots. However, a grand challenge in swarm robotics is that when robot size scales down below 1 millimeter, it is very difficult to keep the independent controllability, especially among a large number of miniature robots. On the other hand, scaling down robot swarms will be beneficial to many areas, especially biomedicine. It is envisioned that hundreds of miniature robots working together could greatly enhance their functions, such as drug delivery and minimally invasive surgery. Previous work has shown cargo transportation and the shape-changing behavior by using magnetic robot swarms. However, it is still a challenge to program complex formations for cooperative functions among a large number of miniature robots. So here, our key research contribution is the development of a design methodology and a proof of concept demonstration to create a cooperative macrorobotic swarm. The swarm has key properties, such as programmable and reconfigurable formations, as well as functions of cooperative manipulation of objects. Our method is to control self-repelling ferromagnetic macrorobots by programming the external magnetic field, both spatially and temporally. The programmed external magnetic field can produce magnetic potential energy and shape and force distribution, such that the overall formations can be encoded into the system equilibrium. For example, these magnetic modules at the air-water interface as robots can aggregate into a ring-shaped formation by controlling these magnetic fields. Our design method follows a systematic procedure to program external magnetic field based on predict models. And this provides a generic approach to create arbitrarily desired formations among a large number of miniature robots. And with this method, we demonstrated versatile formations among more than 100 miniature robots by programming these magnetic potential energy distributions. And moreover, these macrorobots can also work closely and cooperatively for different tasks, such as uniformly pushing long-shaped objects and transporting multiple objects using caging and grasping type of strategies. The swarm also has a special property of being intrinsically soft as a group. The compliant formation allows the swarm to navigate through complex environments by negotiating around these obstacles, such as posts, channels, and hosts. So in summary, we have developed a method to create and control a magnetic macrorobotic swarm with both programmable formations and cooperative functions. This work could have some potential impact in active matter in physics, building metamaterials by self-assembly in material science, and drug delivery in biomedicine in the future. Thanks for your attention.
The third presentation is automated shape-shifting for function recovery in damaged robots by Sam.
Hi, I'm Sam Kriegman, and it's my pleasure to present, on behalf of my co-authors, pictured here, our work on automated shape-shifting for function recovery in damaged robots. Much previous work has shown how an autonomous robot, once damaged, can update its controller for its damaged or injured body. For example, through continuous self-modeling, or by traversing a behavioral repertoire, effective gates can be found for the damaged structure. However, these methods only change the controller, not the shape of the robot, which raises the question, can shape change help adapt robots when damaged? To test this, we optimized the robot to move as quickly as possible forward in simulation. And we built it in reality using 140 pneumatically actuated silicone voxels. Then, of course, we cut off its legs in simulation and in reality. Ouch. The damaged robot can no longer walk, of course. Next, without changing its controller, the robot takes a new resting shape. But it still can't walk. Eventually, the optimizer finds shape changes that undo the damage. And they were instantiated in the real robot system. This robot recovered function through shape change without touching its control policy. And it was in fact slightly faster than the original robot for which its controller was optimized. In another damage case, we cut off the robot's foot. The horizontal axis is recovery time. The vertical axis is relative displacement, where that gray dotted line at 1 is the displacement of the original machine. The red dashed curve is controller adaptation. The green solid curve is the performance recovered by shape change, which, as you can see, for this particular damage case, is greater than that of controller adaptation. We tested 9 damage scenarios in total, in which we lobbed off ever more limbs and chunks of the robot's body. Overall, correcting for multiple comparisons, shape change recovers more performance than controller adaptation. But let's take a look at a few more examples, because it might seem obvious if you're soft and you lose part of your body, you should deform so as to replace that missing part. But if that's the only option, then optimizing shape change is unnecessary. So is regeneration the only option? Well, when this robot lost a quarter of its body, it found a completely novel geometry that synergized with the original controller to recover forward locomotion. And now I'll show 2 very different recovery strategies for the same damage scenario. When the robot's cut in half. On the top, the robot is about to greatly expand its remnant limbs, contract its spine, and flip over. On the bottom, the robot did the exact opposite in the same scenario. It contracted its limbs, expanded its spine for balance, and it moves in the opposite direction because of its shape change. But they both have the same controller. So for more details about this morphology control distinction that we've made, which I think is pretty natural, and our progress on sim-to-real transferability, please ask a challenging question at the end of this session or come see me at the poster. Thank you.
Thank you. The first presentation is reduced orders versus discretized lump system models with absolute and relative states for continuum manipulators, presented by Hadi Sadati. Please.
Hi, I'm Hadi Sadati. Today I talk about reduced order versus discretization approach for modeling continuum manipulators. These creatures are a pain to model, especially when they start doing this. Fast stuff, and that's the modeler state usually. So a model to be useful for control, it needs finite states and robustness. So I disregard finite element approach and purely learning-based approach here. A model consists of these elements. We need to talk about kinematics, continuous or discontinuous, mechanics, Kosterot theory, principle of virtual work, beam theory, or Lagrangian, material mechanics like linear elasticity, finite strain theory, viscoelasticity, and finally the solution, which can be direct or indirect. Well, our contribution, here we present a general reduced order model capable of capturing all the deformation, a discretization approach with absolute states based on Euler-Bernoulli beams, also new derivations for series rigid link approach with non-unit quaternions, and a case of discretization with relative states. Let's start with the differential kinematics. I assume you all know these equations. So when I discretize, I talk about lumped masses connected with links. In the series rigid link case, I have translational and rotational joints. In the Euler-Bernoulli with relative states, I have a beam in between, and strains are the states of the system. And in the case of absolute states, I consider knowing the position and orientation of the masses, so an inverse map is needed to calculate the strains. For the reduced order model, I assume the backbone configuration as a polynomial, and hence the strains can be derived using differential inverse map. For dynamic modeling, I use TMT method, which is a method directly derive the vector formalism of Lagrangian equation of motion for you. Trivial terms, but note the sigma there, so we can calculate the terms independently for each element and then just sum it all. For the compliant elements, knowing the strain, basically the deformation map, we can calculate the transformation map, and then stiffness, damping, and direct input actions related to that. So for experimental study, we used a stiff flop continuum manipulator, 3 degrees of freedom, 3 pairs of pneumatic chambers, and a silicon body. It's like 5 centimeters long. Here is sample results. In the case of external load being present, we have good accuracy, like 5 to 14% for dynamic and 8 to 19% error for static models. In terms of computational costs of derivation, using absolute state is the least complex. Using serial rigid links is the worst, and reduced order model is kind of the same. In terms of simulation accuracy and computational performance, we can say reduced order model is the most accurate and least sensitive. Using absolute state is the most computationally efficient with good accuracy, and using relative states is the least accurate and most sensitive. In general, dynamic simulations are more robust than the static ones. And obviously, we have limitations in terms of theory and application that I would love to talk more about during the poster session. Thank you so much.
Thank you. The last presentation of the section is trajectory optimization for cable-driven soft robot locomotion, presented by James Byrne. James. Yep.
Hi, I'm here to talk about how we can apply differentiable simulation models to soft robotics. Specifically, we're interested in how we can make a robot like this one walk. Now, this robot is made of flexible foam and actuated via cables, which are pulled by DC motors that sit on top of the robot. This makes the robot quite top-heavy and therefore unstable and difficult to control. However, we will show how to leverage a differentiable simulator to find suitable trajectories for locomotion. To start, say we want to model a robot shaped like this. We can start by discretizing the continuum into a finite element mesh with nodal positions x. To model cables, we add unilateral springs to the mesh running through via points and call the vector of cable control signals u. In the static case, we pin the mesh to the ground using zero-length springs. Now, to actually solve statics, we minimize the total energy of the system, and this gives us the quasi-static simulation shown here. Now, to do quasi-static control, we can specify a target position for the mesh x prime and optimize for corresponding control signals. This method forms the backbone of a system that we proposed a couple years ago called soft-IK, where a user poses a soft robot in real time by dragging around target positions for the nodes in a simulation mesh. Here, this is used to do a grasping task. Now let's turn our attention to dynamics. So we're going to use a penalty method for contacts, which applies normal force as nodes penetrate the floor and works similarly for friction. We can adapt our minimization from before to integrate forward in time according to implicit Euler, giving us the stable forward dynamic simulation shown here. Now, to find control trajectories for locomotion, we specify a target trajectory for the robot's center of mass, and will optimize for a corresponding trajectory of control signals. Let's take a look at an optimal trajectory up close. It begins with a preparatory phase that moves the robot from rest and into a cyclic phase, where the robot actually walks. We include 2 copies of this cyclic phase to ensure we find a conservative strategy for motion that continues to make progress after the first walk cycle. The entire trajectory is parameterized with splines. So the simulated robot starts from rest, lifts its hind leg in preparation to walk, and walks forward during the first cycle, continuing to walk forward throughout the second cycle. The overall trajectory transfers from simulation to reality. Now, our overall approach is somewhat slow, but produces useful results. Please see our paper for the complete solution method. Here we show our trajectory for straight line walking, both in simulation and in reality. Here's the same trajectory shot from the side. One very interesting result is that we can optimize for the robot to make a turn, even though it is actuated only in the sagittal plane. Here's the turning motion shot from above. As a final result, we optimize for the robot to walk up a simulated hill. Note how the strategy for flat ground walking from before fails. Our overall goal in this work was to make it easy to experiment with different soft robot designs and locomotion strategies. Here we show a final soft robot controlled using our approach. The process of prototyping this robot in the real world would have taken multiple days or weeks of manual design and control effort. But with our differentiable simulator and trajectory optimizer, we were able to prove the concept in a matter of hours. Thank you.
Yeah, I would like to invite all the speakers to the stage so we can have the questions and answers. So please raise your hand if you have any questions for the speakers. Yes, please.
Hello, I have a question for Sam. The talk about the automated shape-shifting. Do you have actually any video where the robot is moving? I mean, you showed a video where the robot was stationary and just wiggled around, but do you have any video where the robot was actually, the real robot was moving?
Not yet. We're working on this. There are a number of issues that I'll highlight in the poster if you stop by specifically. Right now, the robot just flexes, basically, its muscles. But it's sticky and heavy, and it's difficult to get this to move so far. So the policies of locomotion didn't transfer yet in this paper.
All right, thank you.
You're welcome.
Please in the front.
Also a question for Sam. How do you actually actuate the individual voxels? You had only one air tube coming in, right?
Right, so right now the real robot is only a 1 actuator case. Again, we're working to extend this. So you could put 140 different airlines into each voxel, or the group we're working with at Yale has these pressure regulators that I don't exactly know how they work, but you can use 1 airline and actuate multiple different pneumatic actuators at once. So right now it's just 1 actuator. We transferred specific shape changes that we chose specifically because they could be done just with 1 actuator.
No, also a question. Same person, sorry. So should we all chop off our legs and walk on our hands, or?
If you can shapeshift, sure.
I have a question for Xiaoguang. So how do you specify the shapes or the formations you want?
Yeah, so for the shape, usually we have a pattern, like the user input.
And what is the user input? That's what I'm asking.
Oh, yeah, so for example, you want a ring shape. Yeah. So you just input like a binary map, and then you can encode the binary map into energy distribution function.
So it's an energy distribution function.
Yeah, yeah, correct.
Any other questions? Yes. Yeah, the one.
I have a question for the first talk. So, what is the shortest distance you can trap your magnetic robot?
Currently, the size of the workspace was 5 centimeters by 5 centimeters, and that's constrained by the size of the Helmholtz coils that we have. But we can obviously scale it down if we use bigger sized coils.
Okay.
And the size of the robot was like 1 centimeter.
1 centimeter. Okay, thank you.
Thank you for this interesting presentation. I'd like to ask the fourth presenter. So, how to treat the situation that contacting a human? So the case that adding the disturbance to the flexible part or the changing the model. So how to deal?
So in terms of contact, you can have hard contact or soft contact. Soft contact, so you basically have a spring and damper there, adding to your equation of motion. And you can assume that it only compress. So when it starts extending, you just put it 0. For a hard contact, well, you don't deal with that case usually because it's soft robots, but you can impose a constraint to the system. We can talk more about that. We have problem imposing constraints. Glad that I found people, Joe, working on constraint in the conference.
Yes, one more question in the back. So maybe.
Hello. I have a question for the second author, second paper. So imagine you have an object that you want to circle and it's moving. Do you have to draw the circle all the time? Since your robot doesn't have any sensing ability and it cannot communicate?
Yeah, I think basically if you have a ring shape formation of a collective robots, so they can use a kind of manipulation strategy called caging. So caging is kind of manipulation strategy. You don't need, active tracking of the objects. So it's called, I think, object closure. So it's very robust for this kind of manipulation, especially when the objects are moving or you have multiple objects. That's the strategy we're using for this kind of task.
But you do have to draw the cage all the time.
Depends on the object, if they are trapped inside or they are not trapped inside, right? So if they are not trapped inside, you have to follow the object and trap them. And then you can keep this like a trapping, stably, so then you can trap the objects all the way, reliably and, in this.
But so if they're moving around and then you have to draw the cage all the time.
Yeah, that's true.
Yeah, we have.
I have a question for the last speaker. So how did you minimize the domain discrepancy between the real environment and the simulation environment?
So are you referring to like differences in friction or differences in the robot?
Yeah, some kind of that issue, yeah.
So the parameters that you're looking at are actually pretty nominal in the simulation. You can tune them up a bit to match visually what the robot looks like. But essentially our experience with this particular robot and a couple other simulations and real things we tried is for walking motions like this, if your parameters are somewhere in the ballpark of reality, like not off by more than an order of magnitude or 2, the thing transfers, I think just because the walk is pretty conservative and the soft robot is quite stable.
We can have one last question. Yeah, so please.
Thank you very much. It's for you. The question. I like really your work. It's really amazing how you could do working of completely a soft body with just cables and actuators. Did you have considered like the shaping the feet so that because it cost nothing for you to do it? It's just reshaping the soft material and then keeping exactly the same actuator principle, but probably by reshaping the feet, we would have more stability in the working. Sure. Yeah.
Yes, this is a really interesting question about shaping the feet of the soft robot. So real-world animals use all sorts of things, on their feet, pads, claws, to walk on different surfaces. The feet in this work were picked just because they were the simplest possible feet I could think of. And so you're looking at a flat square, which also happens to be fairly easy to model. I think looking forward to different surfaces, more varied tasks, you're not going to be able to get away with the simple feet that I'm using here. And I think you're going to need both more interesting strategies for feet and much higher fidelity simulation models to capture the actual behavior with the real world between foot and variable surfaces. Thank you.
Okay, so let's, if you have more questions, please fire on the poster, and let's close the session here. Please thank all the speakers again.